So today we'll be discussing the famous Bell inequalities. It's one of the most important concepts in quantum information physics. It has to do with the question, does classical common sense theory describe the world correctly? So this is a much deeper question than just the question, does classical physics work correctly? Because classical physics is based on Newton's equations for motion, Maxwell's equations for electromagnetism, and one or two other things like thermodynamics. But those are very specific questions or theories. Those are very specific theories. One of them could fail in such a way that we could still save the classical theory simply by changing the classical theory, changing the form of the mathematical equations, for example. But it turns out you can ask a deeper question, not about classical physics theory, but just about classical common sense, which is human logic. And it reveals the weakness of our own intuitive understanding of the world, which of course was built up during evolution by common experience. Only when we were able to do recently experiments in quantum physics do we find out that there are some cases where this intuition badly fails. And it's even worse than just saying, well, electrons are waves and particles, things like that, or everything's described by quantum states. It turns out that you can make this conclusion that I'm claiming without ever using quantum physics. And the method is the following. You first use common sense and logic and probability theory to make predictions about some experiments. Then you go do the experiments. The experiments invalidate your common sense logic reasoning. And you don't need quantum mechanics whatsoever to see this fact. People could have done this experiment even prior to the existence of quantum mechanics, and maybe it would have motivated them to invent quantum mechanics. So it also turns out that understanding this point is very essential for understanding how quantum technology and quantum computing works. I see that there might be a question, or maybe it's just the Zoom page. Okay, it's just the Jamboard page, so we'll get there. Okay, let's move on. So as I said, the simplest theory is what's called determinism. Isaac Newton probably thought this was the case, that given a set of causes or any prior conditions, only one possible result could occur. Okay, but what's at the other extreme of this? I made up a little humorous story here. There was a guy named Sage Katzenberg who qualified for the Olympics. And he said, whoa, how random is this? I made finals at the Olympics. So it's like, that's totally random, dude. And I call this randomism. It means that given a set of causes or prior conditions, anything can happen. Any old possible thing. Now, turns out that the world is not like that either, right? You have cause and effect. If you set up a certain number of causes and prior conditions, then you expect only certain possible things can happen. So it turns out that quantum mechanics is the best description of this in-between position. Given a set of causes, the future quantum state can be predicted deterministically because it's controlled by unitary evolution or unitary processes. So we can predict or know what the quantum state will be, and then we can use the quantum state to predict the probabilities of future event outcomes. And not anything can happen, but only those that have high probability under quantum theory. And many things have zero probability, so they just can't occur. Okay, so it's kind of in between point. So these experiments now I'm going to show here today and Thursday are going to be the end of classical probability and what we call inherent properties. So these are some of the questions. What does the psi wave, which means the quantum state for a moving particle, really represent? Is electron a wave? Is it a particle? But we have classical lack of knowledge. We don't know its position. Now, the word inherent property is going to be used a lot in today's session. And for example, position of an electron might be considered an inherent property. So, a particle is either here or there. Whether you look at it or not, it's definitely one place or the other. So its property is inherent. It's well defined within the particle itself. So let's review the concept of inherent properties. So here I made up a little game or experiment where you have a source that's emitting one at a time depolarized photons. Now we know that if it goes to an HV analyzer, it'll have 50% chance to go here and 50% chance to go down here. And then it's going to go through whichever path it goes on. It's going to go through this lower AD polarizer or this AD polarizer. So I want you to write down on a piece of paper or in your head, make a permanent trace of this in your brain and predict what these probabilities are supposed to be. And I'll give you 10 seconds to think about that. Okay, it's easy, so I'm not going to belabor it. It's just 1/4, 1/4, because it's a half and a half and a half. Well, it starts a half, a half, half, a half, 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 half. Okay. Next, let's go to more of a classical situation because photons are kind of quantum mechanics. Let's go back to classical. So we have colored balls, which are, like golf balls or baseballs or any kind of balls. There's a source here, which is producing these balls at random, and each ball can have one of two colors, red or blue, and each ball can have one of two sizes, large or small. So you throw the ball through this machine here. Think of it like a factory, which is sorting, potatoes coming down the line, and it sorts the big ones in the upper direction and the lower ones, the small ones in the lower direction. So since I said 1/2, 1/2, it looks like about half of these balls are large and half of them are small. Now up here goes to another sorting device, which sorts by color, the red and the blue. And the small ones are sorted into red and blue as well. So again, it looks like half of them are red and half are blue. Half of them are big, half are small. So again, if you think about the probabilities here for 5 seconds, boom. It's of course 1/4 again. Now we could change these probabilities here. We could say, let's rebuild this random source and put some biases into here. And then we have a little more interesting problem like 2/3, 1/3, et cetera, 3/4, 1/4. We could work out probabilities, but that's not the point. The point is just understand the idea that these balls have inherent properties, two of them, one is size and one is color, and they're being spit out at random with certain probabilities. Okay. Now the next concept is not inherent properties, but inherent instructions. And the reason for this is I'm trying to build the closest possible analogy with a quantum experiment, but while still staying within a classical experiment. So we have a random source, it's emitting balls, but you're not allowed to look at the balls here. You can only look at the balls at the end. Or another way to say it is all the balls here look identical. That's better. They're medium size and they're gray colored, okay? So if you see one here, it tells you nothing. But inside of each ball, there's a little list, and the list is instructions. It says if you go into a size sorter, you're going to become big or you're going to become small. And if you go into a color sorter, you're going to become red, you're going to become blue. So they don't previously have a size and a color, but they have instructions internally telling them what they will do once they go through this device. So this device is not simply a sorter, but it's also a changer, right? It changes from medium gray, in this case, to large or big gray. And if it has the instruction to become small gray, it goes down here. And likewise for the color. It doesn't have a color, but after it comes out of here, it does have a color, according to its own internal instruction. But notice that each particle or ball has its own set of instructions at the time it was produced. So in some sense, it knows precisely what it will do at the final outcome, even though you don't know that. So those are called inherent instructions. And what are the probabilities top to bottom? Boom, 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 boom. Here, let's run this as a poll. So I put the probabilities here. So In a tree diagram, you multiply the probabilities to get to the final result. Okay, very good. So now everybody got the right answer, which is 1/4, 1/4, 1/4. That's just because I've designed this random source here so that it produces these probabilities. Of course, I could build a different random source that produce set of instructions with different probabilities, but this is just a particular example. It doesn't always have to be this answer E. It just depends on the state of these balls that are being produced. Here we're talking about a classical state, but later we'll talk about a quantum state of photons. Okay, moving on. So can measuring the polarization of individual photons rule out a model based on inherent properties or instruction lists? Okay, very good. I'm going to show the results, share the results, and the answer is people are not sure. Okay, good. That means we can discuss it further. The answer should be actually B, no, as I'll explain now. Here's why I say no. Because if you have a single photon coming from the source going through some set of analyzers, no matter what the set is, and you observe the results, and then you do it a million times and you estimate the probabilities from all those trials, there's no way you can say logically, okay, forget about quantum mechanics. Let's pretend this is the year 1900. You have no clue that light is made of photons and quantum mechanics exists. But you notice that there's these probabilities that are happening because you have 4 detectors or 8 detectors and they're clicking that seemingly random. So you might think, well, Newton told me that light is made of particles. And so if I'm seeing clicks on one detector or the other, that means that the particle arrived at one of these detectors. Well, how did the photon or the particle of light know that it's supposed to end up at this lowest detector here? Well, it must have known that in advance because I'm Newton. I don't believe in everything's random. And so it comes down here. It knows it's supposed to go here, 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 and here. It has a list of instructions. So that certainly is a possible model. You cannot rule out that model logically. Okay, and remember, this is the way physics works. This is the way science in general works. You can't just say that the smart people told me the answer is the following. Therefore, I memorize the answer and I'm going to use that theory from now on. Because the point is, even though they were smart, how did they figure it out? And there were hundreds of really smart scientists thinking about this stuff back around 1900. They couldn't just figure it out from logic. I mean, it was Aristotle 2,000 years ago, or 3,000 years ago, who actually used logic to try to get all the answers, but he got them wrong. The only real way to get the answer is to consider all possible models or theories that could be true, and then simply do experiments to rule out the bad ones one by one. So here's a possible model that you cannot rule out just by this experiment. The model is that every photon, when it's produced, it has a set of instructions like HDV or VDH, telling it in advance where it's going to land. Okay, there's nothing wrong with that model, at least as far as explaining this particular experiment. So see, I'm trying to go logically and gradually here. Now, the problem with this approach is that you could add more and more crystals here. And therefore, the size of the initial instruction list that each particle would have to carry with it would grow exponentially large. And if that were the case, as I say over here, there's no deeper physics theory beyond the list itself. You know, that's my theory of physics. Every particle has a list of instructions. It knows what it's going to do. There's no way I could compress or collapse all that behavior into a simple rule like F equals ma or Maxwell's equations. You simply have the list and that's the end of it. Well, that's a really bad physics model, right? But you cannot rule it out by this experiment alone. Okay, but there is a kind of experiment that can rule out such models. The models based on inherent property tables or inherent instruction tables. And that's where we get to the Bell inequalities. So in order to rule this out, we have to consider two particles, not just one particle. And it's, again, reminiscent a little bit of QKD, because Alice and Bob, they're both making measurements and comparing their results. But the difference is that in QKD, they could do that just with Alice sends one particle to Bob and he measures it, right? But in the Bell inequality experiments, there has to be two photons produced, and we'll talk about that. So the two photons can have strange correlations, which Einstein called spooky, and he didn't really believe in those kind of correlations. He thought there must be something either wrong with the theory, or that these kind of correlations didn't really exist in nature. He wasn't really sure, but he did ask the right questions, okay? But we have to back up and go through classical probability theory again and talk about correlation. Correlation refers to any statistical relationship involving dependence. For example, the age and height in children is fairly causally related or transparently related. So a correlation can be taken as evidence for a possible causal relationship, but cannot indicate what the causal relationship is, if any. And you know, that's all summarized by the famous statement that correlation does not imply causation. So the idea of correlations. Alice and Bob are together initially. They each take a die from a common box. Actually, let's say they each take a sequence of 1,000 dice from the box, and they keep them in order in their own person, so they know the first, second, and third one that they took, and they keep them in order. Then they separate by 1,000 miles. Now, how would you explain it if when they rolled their die each time, and although each number is observed to occur with equal probability, let's say 1 out of 6, because they look random, but nevertheless, they always come up with the same number. Like they both roll it, they both get a 6. Then they both roll again, they both get a 2. Then they both roll again, they both get a 1. How would you explain that? We're gonna go now to the Jamboard. So go to the chat box, click on the Jamboard link, and here we are. Go ahead and propose some answers. There's more than one answer. And type something and think outside the box. Okay, don't think like you're constrained by what you know about classical physics. But don't just make up buzzwords like spooky interaction. Okay. Now here's a coincidence. Could it be a coincidence? Let's say that they rolled their die 1,000 times, and every time they ended up with the same number. Could that be coincidence? Then you say, oh yeah, that's coincidence. So I say, okay, do it again. They do it again, same result. Do it again. Is that still coincidence? Well, I would say no. They must be linked somehow. Well, when and where could they be linked? Is there more than one time and place when they could have been linked or they are linked? Right. Well, the green box says we can explain by averaging their correlations. But what this does is it simply reveals the correlation, and the correlation would always be +1 because they always got the same result. So that would give you no more information than just the very fact that they're correlated. The question is, what could be going on in the universe that actually makes them be correlated like that? Because if they were just regular dice and they were pulled out of the box at random, you wouldn't expect this result. So the blue box says the die have a secret program inside them that moves a tiny weight slightly in a particular pre-programmed sequence. I like that one. And each die would have exactly the same program, correct? And as long as they kept their dice in the right order, then they wouldn't know what was going on, but these dice would always come up the same. I like that one. Okay, then the orange box says maybe they are connected. So that could imply that they're connected later. They could be communicating each time they want to roll and roll in such a way they get the same result. Exactly right. So the pink box and the blue box cover both of the possibilities. Now, somebody typed local realism. So we'll get to that later. But since you've read that, what local realism just means is that the common sense idea that we're operating under. So all these answers we're writing here have to be consistent with local realism. Local means that cause and effect only occurs locally, like within some small region. And realism means that things have inherent properties or instructions. So this is what I'm calling classical common sense. And within that worldview, we can explain this outcome by either the pink box or the blue box. So they're connected, and the connection could either be a prearranged connection, or it could be a connection across space where the dice have little radio transmitters and they're communicating back and forth and their computers are talking to each other. Okay, perfect. So I'm going to go back to Keynote and just summarize these answers, which is exactly what people wrote there. So if this is the case, and nature is classical, and we don't know anything about quantum mechanics, then I'm going to call this kind of behavior rigged. And it's like when an election is rigged. And we hear a lot in the popular media, the mainstream media, about rigging of elections. So it's a good phrase to keep in mind. All right. So now let's talk about correlated balls. So here we have a source which randomly spits out according to some kind of scheme. I shouldn't say randomly, but when you make the final measurements on the two sides, Alice over here and Bob on the right, the probabilities always come out 1/4, 1/4, 1/4, 1/4. So there's some randomness there, but they can be correlated, right? For example, here's a result where you have a big red one and a small red one. But maybe there's some correlation built in. And as we said, the correlation could be rigged either by prearranged programming of the balls in a sequence, or it could be instantaneous, or it could be very fast communication between the two sides. And the balls had internal radio transmitters. Okay, so in classical physics, if you know the state of the pair and you measure one ball, you can predict perfectly the other. So let's say you know exactly how these balls are being pre-programmed with instructions. And then if you know that exactly, and if you know the rule says that if this one comes out big red, the other one has to come out small red, for example. So then if you just measure one of them, you know what the other one is. So that's a correlation. It allows you to predict perfectly what the other one's going to be. But that's only true if you know exactly what the state is. And it's called the joint state, the state of the two balls combined. Okay, now how can we study this in experiments? Well, we need to repeat the experiment many times and get statistics. So here it just shows, 1,000 trials coming out. In this case, I'm showing their properties, big blue, small red, etc. And they're correlated in some manner, which I've made up depending on what the state of the generating device is. But instead of having properties, you could just have instruction sets where you didn't have colors and sizes, you just had instructions, and the colors and sizes just occurred at the ends. So those are equivalent from your perspective. Okay, so here's another example. 2 coins. So Alice has a coin and flips it and gets a result which I call Alice C. Bob gets a Bob C. In the first trial, Alice gets a +1 and Bob gets a -1. So heads is +1, tails is -1. And then they do many trials or runs and they get this sequence of results. Well, do they look correlated? Not so much, right? Well, if these are fair coins, they wouldn't be correlated. So here's plus plus, here's plus minus, here's plus, here's minus plus. They look pretty uncorrelated. But now if Bob has only one coin and Alice has no coin, and Bob flips the coin in front of a mirror, and whatever he gets, he tells Alice, you know, that's your value as well, then they're always going to have the same value, plus plus, plus plus, minus minus, minus minus, plus plus. Well, they're obviously correlated because they're the same thing. That's called a perfect correlation. So here's the same kind of results. This is called uncorrelated, and that's called correlated. And we can reveal that by computing the product. So for each row, we multiply Alice C times Bob C, and we get the product, AC times BC, which is minus 1. Now here we multiply plus 1 times plus 1, we get plus 1. Likewise, if they're perfectly correlated, we do plus 1 times plus 1 is plus 1. Down here we have minus 1 gives plus 1. Notice, in the perfectly correlated case, they're all plus 1. The product is always plus 1. Whereas in the uncorrelated case, half of them are plus 1 and half of them are minus 1. Okay, so if I average all these numbers in the column, I'll get 0 for here, roughly. The average of this product column is roughly 0. If I have enough samples, like 1,000 samples, it'll be pretty close to 0. But in the case of perfectly correlated, they're all plus 1. Therefore, the average is always plus 1. So just by looking, you do 1,000,000 trials, and then you just look at these averages, which are called correlations. The correlation is the average of the product. Here, the correlation is 0. So we took all those 1,000,000 trials and reduced it to one number, 0. Over here, we reduced it to one number, the correlation is 1. So we can see that there's something very different going on between these two different experiments. Correlated, so 0 correlation means uncorrelated. Plus 1 correlation means positively correlated. You could also have a case where the correlation is minus 1. So if Bob's and Alice were always opposite each other, the product would always be minus 1. And if a correlation is minus 1, we usually call that anti-correlated. Okay, is it time for a break? No, not yet. Keep going. Okay, describing a dancer. Now this is a nice example, which I use in the book, and I'm going to use throughout the rest of this session, because dancers have properties and or instructions. So if this dancer has her leg up, and notice I'm just looking at one side, I'm always looking at one side of the dancer. If the leg is up, it's a plus 1. If the leg is down, it's a minus 1. If the arm is up, it's a plus 1. If the arm is down, it's a minus 1. So the story is that the two dancers get together and they talk and they exchange hardware. They do whatever they want to do, okay? Then they go away into their two separate dance halls. Now Alice goes to one dance hall and she observes a sequence of the dancers' moves. Now every 10 seconds on a set clock, she records the value of the leg, which I call Alice leg, Alice C's leg, which is plus or minus 1. And she also records the position of the arm. So Alice sees the arm plus or minus 1. Now Bob does the same thing. He's in a different dance hall across town. And he's on the same sequence of the clock sequence, and he's recording Bob's leg. Bob sees a leg and Bob sees an arm. Okay, so they record these. So here's the Zoom poll. Which of the dancers, for this particular set of recordings, again, a row is a trial. So on the first trial, Alice sees arm 1, leg minus 1, and Bob sees arm 1 and leg minus 1. And then they compute these products. So they have to come together later, right? Because they're far apart. So like in QKD, they come back together later after all the dancing is over. They go to a bar and they pull out their lists and they calculate these products here and make this big table. So let's go to a poll. In the poll, close the poll box. So what I didn't tell you, which was intentional, is that more than one of these answers can be correct. And it's that. So you can see the arm and the arm is correlated because the product is always the same. It's +1. Whereas the arm and the leg is not correlated. You see, in fact, down here, the average is actually very small. It's nearly 0. I actually averaged these numbers here in a spreadsheet. I got 0.04 is close to 0. And if I average these down, I also got a small number close to 0. And if I average these down, I got 1. So see, the 1 means correlated, the 1 means correlated, the things near 0 means uncorrelated. So those are the two, both answers are correct. They're both true. Okay. Now, what could create such correlations? Remember, these are dancers, and the whole story is in effect here. So I'm going back, go to the Jamboard, page 2. So what could create such correlations? Good. So those 4 answers are all the same and they're all correct, but there's another possible answer. So you can add a second possible answer as well. Again, we're still in classical physics because the answers are classical. Right. Bob and Alice are communicating through earphones. That's right. They communicated beforehand, or they could communicate during the dance. That's exactly right. Okay. Excellent. Just like the dice, which had tiny, devices built into them. That's right. So it would be rigged. You could say, well, nobody, like Alice and Bob, didn't know they were doing this little trick. They were conspiring together, and they rigged the whole thing to give Bob and Alice a big surprise when they got back afterwards and went to the bar and compared their notes. Perfect. Okay, so moving on back to the keynote. So we're going to go back to the Jamboard actually, so that you can stay there. There are many possible combinations. Oh no, I need to make a comment here about Q and S. All right. Now, if you read the book, you read about Q and S. Now the story there, it's very important, because if you don't understand Q, then you won't understand the whole point of the Bell inequalities. Okay, so here's the story. Alice and Bob are doing these recordings, and they do like 1,000 rows on the clock. But and the results they get are random, and they record them as random values. But notice there's only 16 possible combinations that there could ever be, right? They could all have +1s. I mean, all 4 measurements could be +1. All 4 measurements could be -1, or any combination in between. But it's 2 times 2 times 2 times 2. That's why I drew the little diagram like this, tree diagram here. But there's only 16 possible combinations. Which one of these occurs at a given trial is random. But every trial must produce one of these, okay? So for each one of these, I've actually calculated in my spreadsheet the products. So here's 1 times 1 is 1. 1 times 1 is 1. AL times BA is 1 times 1 is 1. And BA times BL is 1, okay? And I do that for all these. So down here, I get 1, 1, 1, 1, because they're all -1. And then here, I'll get all the different sets here, depending on the combinations here. Now the question is, what am I going to do? What are Alice and Bob going to do with all this data? They have 4 times 1,000 of these data points. How are they going to analyze these correlations to reveal something interesting. Well, there's many ways you could combine these, right? You could just add them together, plus, plus, plus. So going across a row, you could add all three of those and you get 4. That's called S, is the sum. And here, if you do the sum, you get 1, minus 1, plus 1, minus 1 is 0. Okay, so et cetera, et cetera. I've blocked out some of these for your later enjoyment. Now, but there's other ways to analyze it. It turns out that the sum is not very interesting. I'll tell you why. It turns out that one of the combinations you could do is called Q. I call it Q because it sounds like the curious quantity. Now, it's curious because it's not obvious right now why it's useful. We have plus, plus, minus. So we have 1 plus 1 plus 1 minus 1 equals 2. And here we have 1 minus 1 plus 1 minus minus is 2. Okay. Now the reason we define this Q, and this was first came up, the first person to come up with this was John Bell in the early 1960s. He realized that by analyzing this Q quantity in experiments, we could distinguish between classical probability theory and quantum probability theory. And that's very cool. And he was very smart. That's you know, he had to be to figure this out. Nobody else in the whole world at that time figured this out. And people thought he was a little bit strange for making this kind of a logical argument. So let's go to the Jamboard. On page 3, actually page 3, 4, 5, and 6, go to the page corresponding to your name. And write in, you can use the, see, you can use the pen to write in results. I'm just scribbling here some results. You can write numbers in there. And you can write, you can write 0, 1, 3, whatever you want to write. Then leave a little room for your neighbor to write in their answers. So first do this box, the big box with the S and the Q, but go ahead and fill out all those blank numbers. Okay, good. People are competing there, good. Okay, all right, let's look at page 3. And as far as I recall, those numbers are correct. And you'll notice a very interesting thing about S. Okay, if you look down the column, every number is either 4, 0, or -4. There's simply nothing else there. There could never be anything other than those 3 numbers. Therefore, if I average these numbers in the S column, what can you say, no matter how you sample these 16 possible combinations, if you average all the numbers, say in 1,000 trials, you record the S value and you average them, what can you say about the possible range of the S values? Everybody stay on page 3, and I'll say is the range of S. I'm going to type a question in there. Okay, what is the range of S? Type a sticky note. Okay, and what is the possible range of Q? Well, actually, a range. The green one's not correct. The green one has a 0 in there, and that's not correct because if you average it, yeah, correct. It could be any number between -4 and +4, depending on the probabilities of the different combinations when they occur. No, this is not a 3 in the Q column. There's no 3 there. That's oops. In the Q column, there's +2s and -2s only. Yeah, that's right. But it's not true that the range is -2 or +2, as the top blue one says. The word or is not correct. The range is a continuous range of possible values. Remember, I average all the numbers in the Q column. And depending on the probabilities for which the 2 and the -2 occur, I could get 0, I could get 0.1, I could get 0.3, I could get -0.5. Yeah, good. So now all the answers are correct. Perfect. So you can see I do these exercises not because they're hard math or physics, but so you understand exactly what the logical argument is we're making. Perfect. Let's go back to here. So as we said, S can never be greater than 4. So namely, S is always less than 4 or equal to 4, perhaps. And Q is always less than or equal to 2. So let's just remember this is the theorem, which is absolutely true, regardless of any physics, any mathematics, or anything. Well, simple arithmetic will tell you that if Alice and Bob both record the leg and the arm position on every trial, and they follow this procedure, and they average Q over 1,000 trials, there's no way that Q could ever have a value greater than 2. Okay, so just absorb that statement. It's absolutely true. It doesn't rely on any assumptions or any physics or anything. It's just pure logic. So I think Aristotle would have agreed with this statement, okay? Good. So the reason that we use Q, that John Bell proposed Q as a quantity, is because by measuring it, we can distinguish between classical and quantum physics, which Aristotle would not have known, but it's a very cool fact. Okay, here are the values that you all came up with. Cool. Boom. Now, here's a somewhat different way to calculate Q. You get the same answer. Assuming that we have 1,000 or 1,000,000 trials going down these columns, instead of calculating Q for each row and put a number here and here and here, instead we could just focus on the first row and average the product AA times BA. Now that gives what we call the correlation, right? And for this particular spreadsheet, I rigged it up so that this correlation averages to 0.25. Okay, we know it has to be between -1 and +1, and just in this example, it's 0.25. And this one, I rigged it up so that it's close to 0, and this one's close to 0, and this column averages to 0.083. Again, that's just an example, nothing special about that. I'm just trying to illustrate it. But now if we simply add these together, so here's the formula at the top, the average of Q is equal to the sum of the averages. So average of the first column plus the average of the second column plus and then minus the average of the third column. So here we have, so what is the value of Q? Just work that out in your head or on paper or with a calculator, or estimate it. Write it down on paper or in your head. Okay, the answer is 0.16167. So because there's a minus sign here, right, we have to subtract this 0.083 from this first number. So it's a little bit less than 0.25. Cool. So the point is that, oh, I missed the point. The point is that we get the same result whether we first form the Q here and then average the Qs, or whether we average the correlations and then sum the correlations with the minus sign to get the Q. They're completely equivalent mathematics. Therefore, by this procedure also, average of Q could never be greater than 2, just by pure logic, no matter what the probabilities are over here. So this is the beauty of John Bell's argument. It's just based on pure logic, not based on physics. Okay. Next. Okay, there are some cases where only one of two possible measurements can actually be done on each object. So Alice is looking at her dancer. Now you would think that she could observe and record the position of the leg and the position of the arm. But let's say that the dance hall is pitch black and she can't see anything, and there's somebody who's controlling a strobe light. And that person flashes on the strobe light, and it's a focused beam, and it only illuminates Alice's dancer's leg. Then Alice can only record the leg position and not the arm. And then on the next trial, 10 seconds later, maybe the strobe operator illuminates Alice's dancer's arm. So she records the arm position. So for each trial, she can only record one or the other, but not both. And the same thing is happening in Bob's auditorium. Now, there are some examples of this. For example, I came up with this one: the price you can sell an item for today versus selling it tomorrow. You can't actually know both of these things, right? That's a classical scenario, just like the arm and leg with the strobe lights. Here's another one. It's more of a quantum example. The outcome you will see if you put a photon through a dA polarizer versus putting it through an HV polarizer. You simply can't do both of those and get the answer, because, and you can't do it sequentially because, as we know, when you put it through the first one, it forgets the quantum state that it originally had, so it's not a proper measurement. So what happens in this scenario? See, we're trying to make a classical scenario with dancers that's going to mimic the quantum scenario. So here it is. I've randomly blocked out half of all these possible observations. So in the first trial, this strobe operator illuminates the dancer's arm, and so Alice records the arm position. And in the other auditorium, the strobe operator also illuminates the arm. Okay, but down, for example, in this trial, Alice's strobe operator illuminates the arm, no, sorry, the leg, but Bob's strobe operator illuminates the arm. So notice that on each row here, they can only, when they get together later, after the dances are done, they can only calculate one of these four possible products. So AA times BA, they get it. The other ones, they have no idea because they couldn't record that. So now you can see why it's useful to average down vertically in the columns, because if we have 1,000 of these trials, they can still calculate down here and get the average, which is the correlation. And as long as the strobe operators are operating at randomly, which I say at the top here, if the quantity to be measured is chosen at random in each auditorium and then recorded and analyzed later, this average here should be the same it would be if all these observations were seen and recorded. That's on the assumption of fair sampling. The strobe operator is not conspiring with anybody and is just recording these values. It's just flipping a coin and illuminating either the arm or the leg. And so it's the same thing for each of these columns. They can process the data by averaging down the revealed values in these columns and get numbers. If all is fair and balanced properly, these numbers are the same. So therefore, the average of Q is the same. Okay, it's still 0.167. Okay, that's very important. So here's to summarize. We said that if Alice and Bob can record all the data, namely arm and leg, for every event, then the average of Q could not be greater than 2. Then we said that if they can only randomly observe one of the two variables at a time, and everything is fair and unbiased and not rigged, then when they do the average of Q this way, going down, it still cannot be greater than 2. And again, that's just common sense, logic, and a basic understanding of probabilities and how averages work. Because averages are just adding numbers together. So, you know, Aristotle would agree with this. Okay, average of Q is not affected. Cool. Okay. So here's a Zoom poll. I'll end the poll and I'll close that. And the answer is no, because it's simply what I just said on the previous slide. I'm just reinforcing that. Okay, now Zoom poll 5. I mean, let's consider you had the entire data set in front of you. Let's say Alice and Bob gave you their entire data set. And then you took it away and you spent a few minutes and you blocked out half of the data. Because that's what I've actually done here in the spreadsheet. I took the original data and I blocked out half of them. You can see that half of them are missing on the left-hand side. And I did that in a very tricky way to try to rig the thing. So I'm gonna relaunch it and let you answer again. Okay, so there is not a great amount of agreement here, which is fine. So what I want to do is launch Zoom poll. I'm going to launch Zoom poll 6. Launch poll. In this example, in the table shown, what is the average of Q? What is the value of the average of Q? So yes, it is possible to rig the system if you just take all the data afterwards and select out the good ones that bias you towards the answer you want to get. See, I did it by hand, actually. I did it by hand so that the product of all these is -1 and the product of all these is +1. I just went through by hand and picked them out and did that. So I can rig the results if I want to, if I'm given the chance to do so. But if there's no rigging of that type, then we know that Q cannot be greater than 2. Okay. What is the main result? Yes. Therefore, the inverse statement is that if Q is measured to be greater than 2, then we must conclude the system was rigged in some way. So in the case of the dancers, what does rigged mean? I think we already discussed that. So the dancers could have been pre-programmed in their dances. And I think this is an added point that now we have the strobe operators, and the strobe operators must have been somehow conspiring with the dancers. Because in order to select out those measurement values or those measurement choices or measurement schemes, in order to rig the value of Q to be greater than 2, it's not only that Alice and Bob's dancers have to be conspiring, but also the strobe operators have to be conspiring in order to select out the right values. Okay, good. So if you saw in a result like this, in an actual scenario with dancers in dance halls, and you follow this scheme, I think you could really conclude logically that one of these two possibilities was actually going on. I don't think there's any other way, even logically, that result could lead to Q being greater than 2. So if you believe the world is like that, then you have to conclude that there's some rigging going on. Okay. Now, we're going to do the same experiment with a pair of photons. Here we are. So we have a source that produces pairs of photons. And this is like the source that Henning showed at Q-tools, where we have a blue laser that passes through a crystal, and sometimes the blue photon is split into a pair of red photons. Now these photons may have, well, they have polarizations, right? If you pass this photon through an HV crystal and have two detectors here, you can either get a click on this detector or click on this detector. And likewise for the other photon, which goes over to Alice. Now, I don't want to say too much here, but just to point out that Alice in Wonderland was a character who liked to observe strange things, and point out that it's nice that Bob Dylan actually got a Nobel Prize. So he's a suitable person to do this experiment. That's a joke, by the way. Okay. Well, he did really get the Nobel Prize, though. So really a quote from the book Alice in Wonderland is curiouser and curiouser. So here's the Zoom poll number 7. So half of you thought that there would always be correlations, and half of you thought that maybe, maybe not, depending on the quantum state. Fair enough. Turns out it depends on the quantum state. So it is possible to make a quantum state here that has no correlations between Alice's measurements and Bob's measurements. So that's worth realizing, that quantum physics doesn't always mean correlations. But it certainly makes it possible to have correlations if you construct your source correctly. So let's consider the different sources here. Here's the Sage-Kossenberg source, which is the totally random dude. And so the way he builds a source is that they're uncorrelated. It's just like whatever spits out of here spits out of there. So you can see here that Alice, so that then the scheme or the method is that if the spot hits here, then Alice denotes that by W equals -1. If the photon hits down here, she denotes that by W equals +1. And Bob has a variable he calls Y, and he lists Y as -1 for this spot or +1 for this spot. So that means, as it says down here in blue, we're denoting H polarization as +1, because, yeah, and V polarization as -1. Okay. But really, we record those in the variables called W and Y, which was kind of like Alice arm, Bob leg, etc. Okay. So W is the polarization outcome when Alice measures HV, and Y is the polarization outcome when Bob measures HV. Later, we'll consider other combinations as well. But in this particular example, with the random state, the uncorrelated state, you see there's as many +1s and -1s on both sides. So in this case, the average of the product, W times Y, is 0, which indicates no correlations between W and Y. However, let's now consider a different state that people call it the Bell state, named after John Bell, who came up with this idea. He has a way of preparing, and in fact, Henning will show you how to prepare this type of state in his experiment on Thursday. So Henning can prepare the Bell state, which displays a perfect anti-correlation. So what it means is that whenever Alice observes W as +1, Bob observes Y as -1. Whenever Alice observes W as -1, Bob observes Y equals +1. So that's kind of a cool thing, It's like if this ball is red, this one's always blue, and vice versa. But notice again, all the averages here would average to 0 because equal probability to get +1 or -1 in a column and so on. It's only when you multiply these columns together do you see the correlation. Okay, so in this case, the average of the product is -1 because you can see you multiply this, you always get -1, -1, -1, multiplying like that. Good. So if Alice and Bob did this experiment, came together later and compared the results, they would observe that there's a strong anti-correlation. So this is just a way of translating common sense ideas into mathematical expressions. Now, we get a little more tricky here. What if both of them, Alice and Bob, rotate their calcite crystal by 45 degrees? So they're now measuring a variable on the dA polarization scheme. And the photon either hits the -1 or the +1. So D would indicate a -1. D would be a -1, and A would be indicated by a +1. So this whole crystal is rotated over, and the variable that Alice is going to call this plus or -1 is going to be called X. Bob does the same thing. He has a variable called Z, which he can reveal by rotating his crystal also by 45 degrees. Okay. Now in the X and Z, the experiment was done with these results, as in the table. Remember, when they measured on the HV axis, they always observed perfect anti-correlations. So let's see, what is the question here? What are the outcomes? Are they correlated, anti-correlated, uncorrelated? That's a Zoom poll. Let's run the Zoom poll. And look into the table of results to answer this question. And think about what the value of the correlation would be. Okay, so this one is most people are getting this right. It's a matter of language, perhaps, and in common language you might call this correlated, right? Because they're certainly not independent. But in mathematics, we have to distinguish between positive correlation, which we call correlated, and negative correlation, which we call anti-correlated. So in fact, this is actually anti-correlated, because they're always opposite each other. So if you said correlated, I think you know what you meant, but mathematically it should be anti-correlated. And most of you got that right. Good. Now, what are the product averages here? Let's imagine here that the world was such that both HV and dA schemes would have definite outcomes if measured for each photon pair. Okay, I'm not saying that we could measure, that we actually can measure them or we could measure them. I'm saying let's imagine that each particle had a hidden list of inherent instructions for what this photon would do if it encountered a crystal oriented as HV, and what it would do if it encountered a crystal oriented dA. Now, in reality, only one of those two instructions is going to be relevant. But let's imagine that each photon had its own internal instructions, this photon and this photon. And what I've listed here is not outcomes, but I've just listed those internal inherent instructions. Imagine the world was like this, that photons had these instructions. And each time you produce a photon pair, you get a different set of instructions. The first pair has these instructions. Then later you produce another pair, it has these instructions. And then a third pair has these instructions. And these instruction sets will occur with some probability. You could do 1,000 trials. But then on each measurement, you could actually only measure one of these two and one of these two, actually. One of the Alice's, one of the Bob's. So we're going to, again, to remind you, we're going to denote these variables W, Y, X, and Z. And we're going to think about what the Q value would be under two assumptions. The first assumption would be that all these instructions as shown in the table actually exist and could be measured simultaneously, that you could measure, all four of those properties in each run. And think about what the Q value, would be, or what its upper bound value would be, or its range. I think you'll easily come up with an answer for that. And then think about what would it be if Alice could only measure one of these variables, Y or X, on each given trial, and Bob could only measure one of his values. Sorry, I said W or X, Y or Z on Bob's side. So we'd be blocking out a lot of these possibilities, but still on each trial, Alice would measure something and Bob would measure something. And then they could calculate the product, as we did before over here. Then there would be four possible products, but only one of them would be filled in. And then they would get together later after they filled in this table, and they would average down the column and get the correlation, like the correlation of W and Y they could get. Then they could do another set of runs. They could get the correlation of W with Z. Then they could do they could get the correlation of X with Y. Then they could do another set and get the correlation of X with Z. So after thousands of trials, they could get all four of those correlations, even though they only measured one variable each on each trial. Then, given the correlations, they can calculate the average of Q, right? Plus, plus, minus, and they would get a result. So notice this says we're at the end of our lecture, and we are, because I want you to just go and think about that. Try to understand why this is profound. It took me an hour and a half almost to explain the setup. So what I'm hinting at, of course, is that if they do this experiment and they observe the average of Q greater than 2, that's going to be extremely profound, perhaps one of the most important results ever discovered in science. And it turns out that when you understand this, it forces you to come to grips better with quantum physics. And then once you do that, it allows you to build technology based on quantum entanglement. And that includes, quantum computers, quantum communication, quantum sensor technologies. So that's why I'm going slow here, to get you to understand what the classical common sense worldview would indicate, and that's the local realism that was mentioned earlier. Again, local means that cause and effect can only take place within a very small region of space, not over, arbitrarily large regions. And secondly, that all instruction sets and properties are inherent into the objects. They're not given from outside, because if it was given from outside, then you would say, well, let me just include that outside bit as part of physics. It's dark matter or something weird like that we don't know about, and then we could just incorporate that into our model, and everything would still be inherent and not just popping out of nowhere. So it's not just total randomism. So that's what local realism is. Realism means that all properties and instructions are inherent to the object and not controlled by some outside agent that's rigging it later. In other words, during the preparation of the particles in the source, it can be anything. But once the particles leave the source and travel to two different locations, their inherent properties and instructions are set and cannot be changed unless the two particles could communicate. But since we have localism or locality, we say if the particles are far enough apart, they cannot communicate. The reason for that actually is the speed of light. So we're pretty sure there's no instantaneous communication across, very large distances. So once the particles are separated sufficiently far away, like, at 100 kilometers from each other, there's no way they could communicate, very quickly, like in a microsecond, or I should say a nanosecond. There's simply no way they could do that, according, if you believe in locality. And therefore, once their inherent properties and instructions are set at the source and they travel far apart, they can no longer change those. There can't be any rigging in that view. So you could think about what that means as far as the possible values of Q that could possibly be obtained in an experiment like this using actual photons, and when Alice and Bob use actual calcite crystals and actual detectors. Okay, I think we'll sign off here. Go ahead and keep reading that chapter and think about this deeply. And we'll come back next time. We'll see a demonstration of the experiment, and we'll talk more about, what it really means and how you can use it for quantum technology. Okay, signing off. Bye.